Hello, everyone, and welcome to the plenary session 5B for FRB 2021. My name is Emily Petrov. I will be moderating this session. I'm stepping in for the originally scheduled chair, Maxim Ludikov, who I have no doubt would have done an excellent job in this role in the session talking about the FRB emission mechanism, but I will do my best in his place and get us through this very interesting set of talks that we have scheduled for the next couple of hours. So our first talk is a recorded talk from Kunihito Ioka from the Yukawa Institute for Theoretical Physics in Kyoto, who is speaking about fast radio burst breakouts from magnetar burst fireballs.
Take it away.
Yeah, thank you very much. So good morning, good afternoon, and good evening. And I would like to thank all of you for being here and thank the organizer for giving me a chance to talk. My name is Kunihito Ioka from YITP Yukawa Institute, Kyoto University. Okay, as you know, fast radio bursts are mysterious transient with extremely high brightness temperature. On the other hand, FRBs are also a unique proof of the universe, opening a new field of FRB cosmology. Of dispersion measure and redshift relation is taken from my old paper, very old paper, and and at that time, this relation was just a theoretical, but it is now being a real figure. And related to this, Dr. Takahashi will give an interesting talk on the last session. So please check it out. So today, I would like to consider the following question. What is the ambient density? So in particular, the magnetospheric density, and is it Gold-Rice Julian density or even higher? If it is higher, is it opaque to radio emission or not? And if the density is too high, it may choke the FRB emission. And of course, this is related to the emission mechanism. And also, this is the density, surrounding density is also related to the important question whether where is the emission region, magnetosphere or outflow. So this is a very important question. So in order to answer in order to estimate the surrounding density, this event, so galactic FRB event, is very, very important. And in this event, so X-ray burst is detected simultaneously with fast radio bursts. So in this talk, I would like to conclude that in this event, E plus minus fireball is created, and this leads to a high density of the surrounding, and it makes the system opaque for FRB. So naively thinking, it seems very difficult for FRB to happen in the magnetosphere. But in the second half of the talk, I would like to show that FRB, if it happens, it could break out of this E plus minus. And this breakout condition gives an interesting observational prediction. So the situation is something like this. I consider magnetar and magnetic field, and there is a closed field and also open field. And I consider some burst energy release happens is earthquake, not earthquake, so starquake or reconnection or something like that. And the energy release leads to some electron and positron formation. And this makes E plus minus trapped in the closed loop, closed magnetic field. So this E plus minus is called a trapped fireball. And this is proposed by Thompson and Duncan in 1995. And a famous scenario, a kind of standard scenario for the X-ray bursts from magnetars. And we can estimate the size of the this trapped fireball by using the luminosity of the X-ray and the temperature. And by using the observed value, so the trapped fireball size is around 10 to 4 centimeter in this event. And but I would like to show that in this event, not only trapped fireball, but also an expanding fireball is created. And this expanding fireball release E plus minus outflow and pollutes the surrounding with huge high density. and X-ray is only released after the this fireball expanded and the density decreases. So the reason why this expanding fireball is necessary is that because the density of E plus minus is too high and the X-rays cannot escape from this trapped fireball. And the X-ray can only escape from this E plus minus only after the fireball expands. More detail, we can estimate the optical depth of the fireball by using the equilibrium number density of E plus minus, and we can estimate the E plus minus density by using this formula. And this density is determined by the magnetic field and the temperature of the system. And we can estimate the optical depth of the fireball by using this density and the size, and essentially determined by the Thomson optical depth. Here we include the strong magnetic field effect, modifying the Maxwell-Boltzmann distribution, and also modifies the Thomson optical depth. And here important point is that the temperature is very, very high compared to the ordinary X-ray bursts. And it is around about 80 keV, and the usual bursts have 10 keV, so much higher temperature. And then the optical depth of the fireball becomes very, very high. So this is optical depth at the surface of the trapped fireball, and as a function of the temperature of the fireball. And this is effective temperature. This identified as the cutoff energy of the spectrum. So for typical SGR bursts have 10 keV temperature. So then the optical depth is much, much smaller than unity. So the trapped fireball can emit X-rays, but for this event, temperature is very high, then the optical depth is very, very high. Then photons cannot escape from the trapped fireball. And then so this situation requires that the surrounding field should be open. And if the surrounding field is not open like this, then this fireball just expands. So photons get out from the fireball, but immediately makes E plus minus outside of this initial trapped fireball. So if the field surrounding is not open, closed, then this initial fireball just expand. And this leads to the temperature decrease, and this is not consistent with the observation. So in this burst, the field surrounding the initial trapped fireball should be open like this, and E plus minus can expand to the outer radius. And then this leads to a pollution of the E plus minus at the outer radius. And what is the density of the E plus minus? So this is very simple. And annihilation E plus minus into 2 gamma. This annihilation essentially determines the density and freeze out when the time scale of the annihilation becomes comparable to the dynamical time scale. So the expansion time scale or of the fireball. So the density of the E plus minus is essentially determined by the Thomson optical depth. And this is soleric density. And after this radius, after reaching this density, E plus minus number is fixed. And after later, the density evolves like this, following the dipole magnetic field. So density is given like this. The corresponding luminosity is something like this. So this value of the density is Thomson thick, but it is opaque for FRBs through something like induced Compton scattering, free absorption, or something like that. So system is quite optically thick for FRBs, and it seems difficult for FRBs to be happen. And but system may be like GRB. So in the case of the GRBs, so the central engine also surrounded by large density, and gamma ray bursts observed only after the jet penetrates the surrounding matter. And this may happening also in FRB, and surrounding density of E plus minus is very high density, but FRB may break out this E plus minus. Actually, this may be possible considering the energetics. So maybe the most energetic one is the X-ray burst. This is about 10 to 41 ergs per second. And FRB is much smaller. And on the other hand, E plus minus is even smaller. So FRB may break out the E plus minus. And but here we should be careful because X-ray is connected to the E plus minus through the Compton scattering. And actually this Compton scattering completely controls the E plus minus, and the velocity is suppressed like this, so very slow. And in this situation, so FRB should break out this E plus minus under the Compton drag. So this is a simple estimate. So maybe I don't have much time to explain the details, but less mass energy of the E plus minus is much smaller than Compton cooling energy. So Compton drag is very important. And in order to break out, FRB energy density should be larger than that.
Reminder, you have two minutes.
Okay.
when there's questions, you can.
Okay, so this condition can be plotted like this. This is a FRB luminosity, and this is a X-ray burst luminosity. So this event is something like this. So breakout is possible if the FRB, so if the emission radius is around 10 to 8 centimeters, then the breakout is possible above this line. If the FRB radius is 10 to 9 centimeter, breakout is possible above this line. So this event requires emission radius much larger than 10, about 3 times 10 to 7 centimeter. And this is a giant flare in a galaxy, and at that time there was no FRB emission, and this is consistent with that FRB is choked by the E plus minus. Okay, this is a final slide. So in this talk, I estimate the E plus minus density surrounding the magnetar bursts. And in this event, this is very optically thick for FRBs, but FRB might break out this surrounding matter. Okay, thank you very much.
I know Kunihito isn't here to hear us, but I think, yeah, so I don't think that that he is online to take questions. So I think that the best option is for, if you have questions related to Kunihito's talk, then I encourage you to ask them in the Slack channel and tag him there, and hopefully he should be able to get back to you when it's a more convenient time zone for him. So I think that is we'll end there for that talk and move on to the next one. So the next one is a live talk, which is very nice. So Yajie Yuan will be telling us about plasmoid ejection by Alfven waves, and take it away whenever you're ready.
Let me share the screen. Can you see my screen?
Yes.
Okay, cool, great. Hello, everyone. Really glad to be here. Today, I'm going to talk about our recent work on a possible scenario for fast radio bursts from magnetars. As we know, fast radio bursts are a relatively new phenomenon. They are basically mysterious millisecond duration radio bursts of cosmological origin. So I think I do not need to make the introduction here. So far, we still don't have a very good handle on what sources produce fast radio bursts. But there was one important discovery made last year, is that we detected fast radio bursts from a galactic magnetar, this SGR 1935 plus 2154. So both CHIME and the STARE-2 radio telescopes detected the two fast radio bursts separated by 30 milliseconds. The energy involved in the radio burst is about 2 times 10 to 35 ergs in total. At the same time, there was an X-ray burst coincident with the fast radio bursts. So this is the X-ray light curve seen by integral telescope. So you can see like the overall X-ray burst lasted for about 0.5 seconds. And within the X-ray burst, there are these spikes. And these two especially is coincident with the fast radio bursts. So the total energy involved in the X-ray burst is about 10 to the 40 ergs. So the radio energy is only a small portion of the X-ray burst energy. So this detection has provided a piece of evidence that magnetars can indeed produce at least some of the fast radio bursts. So with this, a natural question we have is, how do magnetars produce fast radio bursts? So far, there are two major classes of models for fast radio bursts from magnetars. So the first class of model assumes that the fast radio burst comes from the inner magnetosphere. In this scenario, a detailed radiation mechanism is still needed to be worked out. Another class of model instead suggested that the magnetars can produce relativistic ejecta, and the relativistic ejecta can run into the surrounding medium and produce a blast wave. So at the short front, the blast wave, there's this mechanism called synchrotron maser process that can produce coherent radio emission. So for this second scenario to work, people usually assume that magnetars can produce these giant flares, and the giant flares can produce this relativistic ejecta. So if we look at the galactic magnetar event, the total energy involved is relatively modest. It's only like 10 to the 40 ergs. So can such a low energy burst event also produce a relativistic ejecta? So that's the question we are going to answer right now. So as we know, a typical X-ray burst from magnetars is believed to be produced by this picture proposed by Thompson and Duncan. Basically, the magnetars may have these star quakes that launch Alfven waves into the magnetosphere, and the Alfven waves dissipate to produce the X-ray burst. So for this galactic magnetar event, we can imagine that it might also be a star quake that has initiated some Alfven waves that propagates into the magnetosphere. So here, the initial Alfven wave amplitude may be relatively small. So at the stellar surface, the relative amplitude of the Alfven wave, delta B over B, can be small, about 5 times 10 to the minus 4. However, if you imagine this Alfven wave propagates along an extended dipole field line to large radius, the relative amplitude will grow with radius as r to the 3 halves. So at about 100 stellar radius, the Alfven wave can actually become nonlinear, meaning that delta B over B becomes larger than 1. So at the same time, we know that the background magnetospheric energy contained in a certain radius basically decreases with the radius as r to the minus 3. So at large distances, the Alfven wave energy may become larger compared to the background magnetospheric energy. In that case, the Alfven wave can actually break out from the magnetosphere. Based on this kind of energetics, we can estimate that the ejection radius should also be about 100 stellar radius. So to see how the Alfven wave actually breaks out, we carried out detailed numerical simulations. Here we use the force-free approximation. So because outside the magnetar, there will be copious electron positron pairs. So these charges will provide necessary charge and current density needed. And because the magnetic Lorentz force is much larger than the pressure and the inertia effect of the plasma, we basically neglect the inertia and pressure of the plasma and basically only consider the plasma moving under the Lorentz force. So this is the force-free approximation. We use our GPU-accelerated force-free code COFFEE to numerically evolve the Alfven waves. So in the first simulations I'm going to show you, we consider a 2D axisymmetry case. Basically, the rotational direction of the neutron star is aligned with the magnetic moment of the magnetar. And we basically launch Alfven waves by perturbing this ring-like region on the star by twisting it back and forth. So this will launch an Alfven wave. So in the movie, I'm going to show you on the left panel, this is the magnetic field. You can see the magnetic field lines, and the color will show the toroidal magnetic field. The right panel will show the current density in the magnetosphere. So as we launch the Alfven wave, initially you can see that the Alfven wave basically propagates out along the magnetic field, But at this radius, the Alfven wave becomes nonlinear. So delta B over B start to become larger than 1. So from this point on, the Alfven wave is no longer confined to the magnetic field line. So they basically just move ballistically outward, pushing the field lines ahead of it and stretching open these field lines behind it. So this creates a current sheet on the equatorial plane where the opposite magnetic field lines meet. So you can also see this from the current density plot. So basically the Alfven wave packet will just accelerate outward, accelerated by the magnetic tension behind it. And you can see lots of small plasmoid are generated in the current sheet. Here we injected another Alfven wave packet to model these multiple ejection events. So basically the Alfven wave will just accelerate outward, and it becomes a relativistic ejecta that run into the Magnetar wind. So this will show you how the energy density and the Lorentz factor of the ejecta looks like. So in this movie, we can see the energy density of the Alfven wave. So the ejecta energy quickly becomes much larger than the background magnetic energy. And here from this plot of the Lorentz factor, you can see that the ejected Alfven wave, this packet indeed is accelerating away from the magnetar. So this ejecta can reach high Lorentz factor, and it will eventually drive a blast wave, basically a shock front, into the surrounding magnetar wind. So we can look at the energy flux as a function of time. So here, this is the space-time diagram of the Poynting flux. So these two bright lines basically correspond to the two ejected Alfven waves. They more or less move at the speed of light. So if we take a cut at, for example, 2 light cylinder radius, we get the Poynting flux as a function of time. So this, the two peaks basically correspond to the two ejecta. And you can see that behind the ejecta, there is enhanced Poynting flux, which decays slowly with time. So this Poynting flux in the tail of the ejecta is actually much enhanced compared to the quiescent magnetar wind. And they only decay on the time scale of the rotational period of the magnetar. And we can see that the angular distribution of the energy in the ejecta is relatively concentrated. Most of the energy is contained within an angular range about 0.4. So we think that in this case, the fast radio burst emission can be produced at the shock front driven by this relativistic ejecta. So the radio is produced by this so-called synchrotron maser process, where you have the upstream cold plasma run into the shock front and see the compressed magnetic field, and the particles start to gyrate coherently to produce the coherent radio emission. We find that the energetics can roughly agree with the observation when the radio bursts are produced in these shock waves, and the gigahertz emission comes from a radius about 10 to 13 centimeter. Now, how about the corresponding X-ray emission from this burst event? So we think in this kind of scenario, the X-ray emission can naturally be produced by the magnetic reconnection event behind the relativistic ejecta. So this is the region I'm referring to. So we can see that as the Alfven wave ejects from the magnetosphere, it opens up these magnetic field lines and form a current sheet on the equatorial plane behind the Alfven wave packet. So you can see a lot of small plasmoids are generated. This is basically the magnetic reconnection process where the opposite magnetic field lines change partner and release the energy. This is basically a rough diagram of how the magnetic field reconnects. So this can heat up the plasma and produce the X-ray emission. So you can also see that this current sheet extends all the way into the ejecta itself. So this portion actually moves relativistically with the ejecta, and the dissipation here will produce beamed X-ray emission.
3 minutes, Yajie?
Oh, sure. We use the numerically dissipated energy as a proxy to look at how the X-ray light curve looks like. So this is basically the sky map as a function of the observer angle and the observer time. Here is the light curve seen by an observer located at this angular range. So most of the X-ray actually comes from this relativistically moving portion of the current sheet. So you can see that most of the emission comes relativistically beamed into these two spikes, more or less coincident with the radial bursts. Okay, so what I showed you before are 2D simulations where we have this ring-like region of perturbation where Alfven wave is launched. So in reality, the Alfven waves may only be launched from a small region on the neutron star surface. For example, here, imagine there's this small patch that is disturbed by the star quake and launch Alfven waves. So to see how this might work out, we carried out large-scale 3D simulations to look at whether an Alfven wave packet launched from this kind of localized small region can also produce an ejecta. So the answer is yes. So in this movie, I'm going to show you this color shows the energy density of the magnetic field, and these green lines are magnetic field lines. You can see that when we twist up this region and launch a toroidal portional Alfven wave, it can also break out from the magnetosphere as long as the energy is large enough. So in fact, in this 3D case, the needed energy is smaller than the 2D axisymmetry case because the Alfven wave packet only need to open a portion of the magnetospheric field lines. And here is actually just a slice on the y=0 plane showing the ejecta. So we can see some feature that is very similar to the previous 2D simulations we see. Especially, you can see also this current sheet on the equatorial plane that have a reconnection happening and a lot of small plasmoid generated in this current sheet. So this region can also produce dissipation and X-ray emission. Here is another view showing the magnetic field in the ejecta. And also we looked at the angular distribution of the energy in the ejecta. So it is relatively compact, although it's not like super concentrated, but the energy is basically mostly concentrated in an angular range, not larger than 0.5 stellaradian. Okay, I just wanted to show you another plot of basically the current density distribution in the magnetosphere as the ejecta moves out. So here is basically the volume current carried by the ejecta itself. And you can see like behind the ejecta in these regions, especially on these field lines separating the closed magnetosphere and the open magnetic field, these are the regions where the current is concentrated, and they could have some dissipation as well. And on the equatorial region, the reconnection produce all these flux tubes you can see in the current density. They can produce this dissipation and the X-ray emission. Okay, so just to quickly summarize, we have shown that even with these low amplitude Alfven waves launched by star quake, they may be able to produce relativistic ejectas when the wave propagates to large distances of the outer magnetosphere. And the wind behind the ejecta can be significantly enhanced. And the radial burst can be produced by synchrotron maser at the shock front, while the simultaneous X-ray burst can be produced by dissipation in the current sheet behind the ejecta. So I will end here and I'm happy to take questions. Thank you.
Thank you. That was a very nice talk and some very beautiful simulations. It's interesting work. We already have a few questions coming in the Q&A. If anyone else has other questions, start typing. Okay, so the first question is from Wenbin Liu. Is the angular size of the escaping plasmoid, i.e. about 0.5 radians, directly given by the angular size of the Alfven wave injection region on the neutron star surface?
So I think it's slightly different. So actually, here the so firstly, the Alfven wave will follow the dipole field lines, and they follow the expansion of the dipole field lines, and then at the ejection point, they will launch from that already expanded angular size. And afterward, the Alfven wave the packet will roughly follow spherical expansion and with a fixed, more or less fixed angular size. So it depends on, like, at the ejection point, how much the Alfven wave has expanded. Yeah.
Great. Okay, next question is from Bing Zhang. How do results depend on the inclination angle between the magnetic and spin axes?
Yeah, that's a good question. So right now we have the spin axis aligned with the magnetic axis. So in the inclined case, you will have a striped wind coming out from the neutron star, and the ejecta might interact with the striped wind. Yeah, this is something we haven't tried to simulate yet. I think that's definitely an interesting scenario to consider further. Yeah,
for sure. Okay, we have one final question in the Q&A from Pawan Kumar. Very nice talk and very pretty simulations. Do you expect the X-ray peak before the radio according to your model?
Yeah, thanks for the question. So here, we think that the radio will basically, so the ejecta will move at a speed very close to c, and so the radio emission will come from, yeah, it depends on how fast the ejecta moves. If the radio is emitted at, like, the shock front, the X-ray is emitted from relatively close to the magnetar, so it basically travels out as at speed of light from that point on. Yeah, so it depends on the Lorentz factor of the ejecta itself, I think. So it's, yeah, we haven't. So in our current simulations, we kind of assume that the ejecta moves with more or less at speed of light. So the two will arrive more or less simultaneously, although the X-ray might be falling behind a little bit. But it will depend on the Lorentz factor of the ejecta itself. I think it needs some more study here.
Yeah, so yeah, that might mean that the X-ray would peak before the radio in the, like, I guess in the model nearby, the X-ray and the radio may be sort of cotemporal, but then, if there's dispersion or something like, or are you saying that the X-ray and the radio would peak at the same time at the source? I think Pawan is trying to ask if the X-ray would peak before the radio or after the radio, given the results of the X-ray and radio flares of the SGR.
Right. Yeah, the X-ray emission is slightly could be slightly behind the radio as well.
Okay, excellent. Okay, I don't see any other questions in the Q&A, so we can move on to our next talk. Thank you, Yajie.
Thanks.
Okay, and then our next talk will be a recorded talk, and that will be by Navin Sridhar, who will be telling us about shock-powered coherent radio precursors of neutron star mergers.
Okay. So
what happens during a merger event is of fundamental importance. One of the goals of multi-messenger astrophysics is to understand the equation of state of neutron stars, the R process nucleosynthesis, formation of jets, and so on. And in the case of neutron star and neutron star black hole mergers, they encode key information to these properties of neutron stars and R process nucleosynthesis. So if you have gone through this paper, there are many comparisons to FRBs that I draw here, but the goal of this was not to explain all FRBs per se, but to see if from first principles, any FRB-like coherent radio emission is indeed expected to be produced from neutron star mergers. So the kilonova and non-thermal counterparts of, say, JW 17017 are chiefly the result of large mass ejection and jet formation, which take place after the completion of merger. Compared to the post-merger phase, less theoretical work has been dedicated to EM emission during the late in-spiral phase prior to the coalescence. Nevertheless, the discovery and characterization of such precursor emission would be of great importance to learn the pre-destruction properties of the source, say like the magnetic field of the neutron stars. Even to monitor the post-cursors like the kilonova, one needs proper localization, which gravitational wave events alone cannot supply. And just a small fraction of the mergers are seen with short GRBs due to their beaming. They can only be seen along with gravitational waves up to, say, 200 megaparsec. Another reason why we need to study precursors is to study massive mergers, that is, neutron star merging with massive black holes. From this, you can see that only those black holes that reside to the top left part of this figure with a specific spin and with a specific mass can produce a disruption of the neutron star and hence an electromagnetic signal. And any black hole much heavier than whatever is not in this region will not produce any disruption because it engulfs the neutron star as an entire body, and therefore no emission will be produced. So whether the resultant emission during the in-spiral phase is FRB-like or not would be very interesting to study, and let's look more into it. Anyway, a radio precursor is more interesting than a short GRB because radio telescopes are more sensitive than gamma ray telescopes to be able to detect events even from gigaparsec distances. So what is the mechanism that we envision here? The ingredient is that we need at least one magnetized neutron star. In the right panel, what you see here is one magnetized neutron star and a companion. The companion can be a neutron star or a resistive subject like a black hole. So, and these are the field lines. The cylinder that you see is the light cylinder of the black hole, and the companion is well within the light cylinder. That is the region that we are envisioning here. And the bottom panel is the top-down view of the system undergoing in-spiral phase. The orbital acceleration of the highly magnetized neutron star around the companion is a source of electromagnetic power that arises due to the magnetic dipole radiation, which is independent of the properties of the companion, whether it's a black hole or a neutron star. This is similar to what Kunihito, Ioka worked a couple of decades ago, and recently by Carrasco and Shibata. So in an isolated pulsar, the field lines typically open only beyond the light cylinder. However, when you have a resistive companion inside black hole, like inside the light cylinder, it opens up much more field lines compared to an isolated pulsar, the left side, like over here. The binary pulsar wind is carried along the open field lines over here, whose power increases as the orbit shrinks. As the companion comes closer and closer, more and more field lines are open, and therefore the wind power also increases as the orbit shrinks. And a fraction of this power is dissipated by heating the particles, and the rest in the form of Poynting flux along the open field lines. The binary wind over several orbits, they trace a spiral pattern beyond the orbital separation, with the smallest spiral being emitted at later times, also carrying the largest Lorentz factor and the highest power. This accelerating magnetized wind ejecta can create internal shocks in the binary plane and can create synchrotron maser instability. Therefore, the emission is beamed along the equatorial or the binary plane here. This is just a schematic of synchrotron maser instability, which you all came across earlier. So here I will quickly run through some of the analytics before jumping onto the methods and results. The effect of close orbiting binary companion, be it a neutron star or a black hole, of a given radius is to increase the wind power as the merger proceeds, right? A constant fraction of this wind power emerges as a quasi-steady magnetized wind from the binary along the binary equatorial plane, and this wind power is a very steep function of the separation, binary separation. It goes as 8⁻⁷. And the other important parameter is the gravitational wave coalescence time, which goes as 8⁴. That is the binary separation to the fourth. And the next parameter is the wind mass loss rate. For ordinary pulsar winds, the wind mass loss rate m dot is typically normalized to the Goldreich-Julian value. However, since we are modeling, here we are modeling the mass loading flux with an unknown parameter m here, m. We do not really know how the mass loss rate goes as the binary separation radius, because the external wind environment can be drastically different from an isolated pulsar wind only for which the Goldreich-Julian value holds. So this is an unknown parameter m, which encapsulates the wind mass loss rate. So from this we can derive what the Lorentz factor of the emitted wind will be at different orbital separation a, and this would just be E dot over m dot c square, and it goes as 8⁻⁷. Note that here we are assuming that the sigma problem is solved, by which I mean the wind power is entirely converted. The wind has nearly fully converted its magnetic energy into bulk kinetic energy, and very less is still in its pointing flux. Otherwise, there would be E dot over m dot c square to the 1/3. So we're not considering that because there are many observational evidences that show that from pulsar wind nebulae that reveal that at least by the location of the wind termination shock, the wind has nearly fully converted its magnetic energy to bulk kinetic energy. So we model how the wind evolves with time during the merger event, given the prescription I mentioned before. We consider certain starting separation and then ending separation. So this is how the separation radius evolves over time. This is how the wind mass loss rate evolves for different m parameters that encapsulates the mass loss rate. This is how the wind power and wind Lorentz factor evolves for different m values, for different models of the wind. So in our work, we consider two broad cases for the wind mass loss wind models. The first is m equals 6. M equals 6 gives rise to the hosting fast shell. And the second thing that we consider is for m equals 5. For all m less than 5.5, you see that the fast shell decelerates, unlike for m equals 6 cases. Note that m equals 3 corresponds to the typical Goldreich-Julian value, and m equals 7 produces no shocks. So that is of no interest to us. So we take m equals 5 and 6 as a representative of these two broad cases. So with this, we implement these models into a relativistic hydrodynamical code and follow the shock interactions and see how the shock evolves and the fluid properties evolve as we go on. M equals 6 is a special case because we can derive analytical solutions of the shock properties, which we then use as a test bed for our code. And then we totally rely on the code for the non-ideal m equals 5. So why do we call m equals 6 to be the ideal case? That's because the upstream here is not already shocked when the fastest shell sweeps through it. For m equals 5 and below, m equals 4, 3.5, for example, we can expect the upstream medium to be already shocked and therefore perhaps be hotter which can cause some problem to synchrotron maser emission process. We test these scenarios with our simulations. These are just some numerical simulations. I'll go to the next one. Here what you see is the time evolution of some important hydrodynamical quantities for the considered two regimes of wind models. The top panel is this is the time evolution. Top panel is for the upstream density, shock Lorentz factor, bolometric shock fluence, specific internal energy for the decelerating case, that is m equals 5, and a coasting fast shell case, that is m equals 6, black lines. You can see that the m equals 6 ideal case match very well with the theoretical expectations, the dotted curves very well. So we think that the wind models are properly implemented in the code, and our m equals 5 red curves are also reliable. I would like to draw your attention to the last panel here. Note that the upstream temperature or the specific internal energy is low enough even for m equals 5 case, that is with some shocks already in the upstream region. So even if you have certain micro shocks in the upstream region, when the fast shell passes through it, it's not really going to suppress the synchrotron maser instability. That's what this panel shows. So what can we do with these? With the upstream density and shock Lorentz factor, we can get nu-P, that is the plasma frequency, upstream plasma frequency. This can then be combined with the synchrotron maser spectra and its emission efficiency derived from peak simulations. And that's what we are going to do here. The left panels here, they show the black curves show the synchrotron maser spectra, and the bands here show different frequency ranges, basically. At the top, the top one is at earlier times, and the bottom panel is at later times. What we see is from the position, so we use the plasma frequency, and then along with the efficiency and the spectra obtained from peak simulations, we can obtain the radio light curves at different bands here. So you can see from the position of the frequency bands.
3 minutes left.
Yeah, thank you.
Thank you.
So from the light curves here, what we see is that the higher frequency band peaks earlier than low frequency, which arrives later. This is also captured here in the dynamic spectra or the waterfall plots. I'm calling it an FRB here because it has several key properties of observed FRBs. The major difference that you see between the m equals 5 and m equals 6 different wind models is that the drift rate is different, and then the duration of the FRB is also different. So this is for m equals 6. What we m equals 6 for an observed frequency of 1 gigahertz, we can use observations by retrieving the FRB's energy and timescale to pin down what the magnetic field of the pre-merger neutron star is. Note that for even larger mass loading parameterized by m here, like I said before, for larger m, the duration of the FRB increases. The pulse train can even be up to a few seconds. One can also naturally expect the FRB signal to carry some periodic sub-features modulated by the orbital period at the time of evolution, as can also be seen from the recent example. Another point of these simulated FRBs is that the frequency substructures that you see here are a natural consequence of the non-smooth features seen in the synchrotron maser spectra. And the break in the drift rate that we see here is also a characteristic feature of many FRBs. With this, I will try to wrap it up here. We have proposed a concrete mechanism to transform a significant fraction, say 10 to the minus 3, of the total pointing energy released by the gravitational wave inspiral of a magnetized compact object binary, say a neutron star or neutron star black hole merger, into a burst of coherent radio emission. So yes, we can perhaps expect an FRB-like emission as a precursor to a kilonova. The emission will be beamed along the orbital plane. Therefore, we can spot these coherent radio emissions even when a short GRB is not seen, because short GRBs are emitted perpendicular to the equatorial plane. And essentially, we will see it only when a short GRB is not seen. This can be produced for any magnetic field strength greater than 10 to the 12 cos, and we can expect a fluence of around 1 Jansky millisecond from gigaparsec distances, and they can be detected using existing radio survey telescopes. Indeed, such merger counterparts could already be lurking in existing FRB samples, as these mergers can account for around 1%, say 40 to 50 per day of the total all-sky FRB rate. Out of them, we can also predict at least 2 of them to be detected contemporaneously with gravitational wave detections per year. The intergalactic delay time between a gravitational wave and a burst from 100 megaparsec away at 1 gigahertz is around 0.4 seconds. This will be several tenths of seconds if we detect bursts at lower frequencies, say 100 megahertz. Yeah, so I will stop here and take any questions. Thank you.
Okay, that was a really interesting talk. Unfortunately, I don't think that Navin is online to take live questions, and I don't see anyone from his team online either. So if you do have questions, you may just have to put them in the Slack channel and tag Navin for further follow-up. But that's probably the best way to do it. So we can just go ahead and move on. We're actually to time anyway. So we will move on to the next recorded talk, which is going to be given by Alex Cooper from the University of Amsterdam, talking about coherent curvature radiation.
My name is Alex Cooper. I'm a PhD student at the University of Amsterdam. And today I'm going to talk about some work that we've done on coherent curvature radiation, specifically looking at maximum luminosities and high energy counterparts. And this is work I've done with my supervisor, Ralph Wires. So I think during the conference, we've seen this plot quite a few times, but just as a refresher, coherent emission is required when radio transients are too bright and too short to be explained by individual particles radiating alone. And this is nicely displayed here. So on the x-axis, we have the duration of the transient. On the y-axis, the spectral luminosity in the radio. And you can see this white section of the plot is full of transients, especially from neutron stars, that we think require coherent emission. And so this is what we're aiming to explain. So how do you make coherent emission? So there's 2 very general classes of models. So firstly, we have the maser-like or plasma models that have been discussed already in this session. And I'm going to focus on the second type, which is the antenna models. And these models require the physical clustering of particles within one observing wavelength. So if you're observing with meter radio waves, particles within a meter or so of each other in the observing frame could act coherently. And the idea here is that if the emission, if these particles are close enough together, the emission is in phase, and therefore the power of the emission goes as the number of particles squared instead of just the sum of the radiation. So we can look at what we require for these kinds of models. Specifically, there's 2 main criteria, 2 necessary conditions. And the first, as I said, is spatial confinement. So the particles must be within one wavelength of each other, and in the observing frame, this is the Lorentz factor of the particles times the observing wavelength. And secondly, the particles must be well aligned. So their momentum must be aligned up to a factor of 1 over gamma. What we'll do is we'll use these conditions and look at the electromagnetic interactions between these particles to say something about what kind of emission we can see. So we think there's 2 main consequences of this electromagnetic interaction between coherently emitting particles. Firstly, we think there's a maximum luminosity that each bunch of coherent curvature radiation can produce. That depends on your source and also spans over many different luminosities. So it could explain lots of different luminosities and timescales of transients. And secondly, we think that there's always going to be a non-thermal counterpart at high energies for radio bursts or pulses that are produced by coherent curvature radiation, which could explain some multi-wavelength observed results. So what is coherent curvature radiation? So as I said, it's an example of an antenna model. And there's a sketch down here on the left. So bunches of charged particles travel along magnetic field lines close to neutron stars. And they travel along these field lines because any motion perpendicular to the field lines is very quickly radiated away because of this very strong fields. And it's the slow curvature of these field lines as these particles move down them that leads to an acceleration similar to circular motion. And this acceleration leads to radiation, which is curvature radiation. So this has been known about for a very long time, and it's been used in models of pulsars and pulsar magnetospheres. And more recently, it's become an interesting model with which fast radio bursts could be produced. So as I said before, this is or can be a coherent emission mechanism, and therefore the emitted power of one bunch scales with the number of particles squared in the coherent region. And it also depends on the Lorentz factor of the particles to the 4 and rho to the -2. And this rho is the curvature radius, which is a measurement of how tight these field lines are. And I should also note, as pointed out in a recent paper by Lutikov, the observed power is higher than the emitted power from one of these bunches by a factor of gamma squared. And this is because the emission is tightly beamed into a small solid angle. So let's look from behind one of these bunches. So the big circle in the middle here is one of these bunches of particles that's going to move into the page along the neutron star magnetic field lines. And we can see the maximum size here. And as these particles are accelerated into the page along these field lines, they're going to produce a current density. And this is proportional to the number density of the particles and the speed that they're going out and the charge. And we assume that they're accelerated close to the speed of light. And Maxwell's equations tell us that any current density induces a magnetic field. So this is proportional. You can see the direction of this induced perpendicular magnetic field here. And this is proportional to the size of the region and the current density. And so we can plug these things in because we know them and find an expression for this induced perpendicular field. And here we've changed to the observing frequency instead of the observing wavelength. So what does this mean for the particles? Well, as we said before, these particles are going to follow the magnetic field lines. However, now we have this new component of the field, this induced perpendicular field. And so the total field line is now a sum of the neutron star magnetic field and this induced field. And therefore, these particles are going to have slightly perturbed paths. So perpendicular motion is radiated away, so they are tied to these field lines. So they're going to follow these spiral-like paths. And this is what the magnetic field will look like. Of course, this is exaggerated. But these particle motions are going to look something like this. And another way of looking at this, so although they're following the field lines, it looks somewhat like they're following the neutron star magnetic field with a very small pitch angle alpha. And this will be important later, and alpha is given by the ratio between the induced field and the neutron star magnetic field line. So what does this mean for the bunch of particles? Well, there's a couple of things. I think firstly, if we remember what we said earlier in equation 2, the particles must be aligned within a factor of 1 over gamma. And therefore alpha, which is this pitch angle, should also be smaller than 1 over gamma. And so by rearranging, we find that for coherence to be maintained, this neutron star magnetic field, the local magnetic field value, should be larger than the induced field by a factor of gamma. And this is also derived in Kumar et al. In 2017. So what we can do is plug in our value for the induced field and find a maximum Lorentz factor of these particles. So if the coherently emitting particles are accelerated to higher energies than this, then coherence is destroyed and these won't be visible as a coherent radio transient. And this thing depends on the neutron star, the local magnetic field, observing frequency, and the number density. So we can look at what this means for the bunch as a whole. by considering the luminosity of the bunch. So we know that it goes as the number of particles squared times the emitted curvature power per particle. And we can plug in the values that we know. So we have this condition for coherence on the size of the region, and also plug in the maximum Lorentz factor. And so this gives us a maximum coherent luminosity or curvature luminosity for these bunch of particles that depends on all of these source parameters. So we have the surface magnetic field, the pulsar period, the curvature radius, your observing frequency. This parameter here, the pair multiplicity, is important. It's a measurement of the number density of the particles, and I think that's relatively poorly understood. So we parameterize it in terms of the Goldreich-Julian density, and then the distance from the center of the neutron star. And the maximum luminosity that these bunches can produce depends very sensitively on this distance, because the magnetic field drops off as you go further away from the neutron star. And so this is one of the reasons we think that bright coherent emission, if it is powered by coherent curvature radiation, should occur close to the neutron star surface. So we can plot this thing. So on the right, we're going from the total luminosity on the last slide to the observed spectral luminosity by multiplying by gamma squared and dividing by the critical frequency. And we've plotted these maximum spectral luminosities. So on the x-axis, we have the surface magnetic field of different types of neutron stars. And on the y-axis, we have the spectral luminosity. And in the background, we've plotted kind of typical sources. So FRBs, the most bright, giant pulses, and also these interesting new intermediate sources that have been discovered recently. And so these lines refer to the maximum luminosity that bunches at the surface of these magnetic field strength neutron stars can produce given some parameters. And of course, this varies depending on the period, the curvature radius, but also there's a few others. So now I'm going to move on to the second consequence of this, and that's the high energy emission. So as I said before, individual particles are going to follow these corkscrew or spiral magnetic fields. And although they're following the field lines in terms of the particle acceleration, this is identical to synchrotron radiation with a very small pitch angle. So what's happening here is there's two very different, there's acceleration on two very different scales. So the large scale bunch of particles moves along these field lines, these curved field lines, and produces coherent radio emission. But without breaking those conditions for coherence, individual particles are gyrating on small scales. So they're gyrating along these field lines, and this will produce incoherent X-ray emission. So we can do the same thing and look at the number of particles in this bunch multiplied by the emission or the synchrotron luminosity per particle to find, again, dependent on all these parameters, what do we expect in terms of X-rays? And we think that this should be visible with all coherent curvature radiation powered pulses. So what does this mean for observations? So using the equations that we had a few slides ago on the maximum luminosity of coherent curvature radiation, if giant crab pulses, for example, were powered by coherent curvature radiation, they must originate within 200 kilometers of the surface. And the brightest nanoshots must come from less than 50 kilometers from the surface. And that's because you need that strong magnetic field close to the neutron star to support the coherence. We also think that the recent nicer result of an X-ray enhancement during crab giant pulses could be explained by this simultaneous X-ray emission. And also there's some potential for the SGR 1935, the Galactic FRB, as was mentioned previously in this session, the X-rays that were observed during the FRB had a very different spectrum to the other magnetar bursts that were seen around the same time. And the idea here would be that because the same radiating particles produce both the coherent emission and the high energy X-rays, you would see only this non-thermal component when you see the radio emission. And otherwise you would just see that thermal component that's more isotropic. In terms of fast radio bursts, we agree with Kumar et al. 2017 that fast radio burst strength emission, so the very brightest coherent emission that we see, should come from the surface of magnetars if it's powered by coherent curvature radiation. And of course, there's dependence on many other source parameters. And we also predict a non-thermal X-ray component for all observed fast radio bursts if they come from coherent curvature radiation. And this would be in addition to a thermal component, and this thermal component might be larger, of course, but this could be detected. And we also think there would be an MEV cutoff due to the high energy photons interacting with the strong magnetic field in the vicinity. And radio X-ray fluxes or even limits could pinpoint both the emission location and maybe some of these unknown parameters. Okay, some caveats to the model. Of course, the model in general, bunching of charges is very difficult, and there's a nice lightning talk by Max Luzakov on the topic. Specifically for our work, we've only considered spherical geometries of these patches. And so you can get brighter emission, for example, if the source is extended longitudinally along the line of sight. Our predictions are for maximal bursts, so bursts where the Lorentz factor is equal to this maximum Lorentz factor that we derive. And also we've only considered a dipole magnetic field. In terms of future work, I think linking the Lorentz factor of the particles and the observation frequency would add additional constraints, and this is something we haven't done. Also, of course, considering different patch geometries would be very important. And I think very interestingly, you can start to constrain some of the parameters using sensitive X-ray limits of bright or close by fast radio bursts, or indeed galactic bursts. So yeah, in the conclusion, we think there's a maximum luminosity of coherent curvature radiation, as I said before, and we think there's always going to be X-ray counterparts for pulses powered by this curvature radiation. Thank you very much.
All right, that was a really interesting talk. I don't believe that Alex is on the line at the moment to take questions. I don't see anyone from his team. So I would suggest that you put all of your comments and questions that you have for Alex in the Slack channel, and he will get to them at some point. So yeah, please tag Alex with questions over Slack. And we can move on to the next talk, which is also going to be a recorded talk. And this is by Marisa Geyer, who is at the South African Radio Astronomy Observatory, talking about FRB-like emission from a young pulsar. So go ahead.
Go ahead.
All right. So yes, first, thank you so much to the organizers for giving me an opportunity to present work on a pulsar here at the FRB conference. I hope to show that it's got some interesting properties, quite overlapping with some of the FRBs that's already been discussed in detail here. And this will be quite a data-driven talk, so I'll show you some of our MeerKAT results. This work has been done in collaboration with the MeerTime team. So some of their names are up here. And then also with my colleagues over at Soraya, where we are working on the commissioning of the MeerKAT telescope. So for us to get started, I would like to just introduce a couple of characteristics on this particular pulsar. So 0540 minus 6919 is often thought of as sort of the twin of the crab. And in this PP dot diagram, you can already see why it kind of co-hosts in the same environment. I'm just struggling to get my cursor up. This particular pulsar was discovered in the X-rays, and so back in 1984 using the Einstein telescope, and it took about 9 years until we had radio emission from it. So in 1993, Parkes finally saw weak radio emission from it at about 600 megahertz back then. And just to summarize some more of the overlapping characteristics with CRAB, you can see that it has a similar pulse period and also a similar characteristic age. So a young pulsar estimated to be about 1,600 years old. And just like the crab, and like we learned quite a bit about in the previous talk, this pulsar emits giant pulses. And so it's exactly these giant pulses that I want to talk to you about and the observations we have for that using Meerkat. So before I continue, maybe let me just state what we mean with giant pulses here. So they are short duration, bright single pulses from pulsars, and they often occur in narrow phase windows. But like you will see, this requirement is somewhat relaxed for O540. As the name obviously also suggests, they are brighter than what's considered typical. So if you think of the distribution of the pulse energies for a normal pulsar, we tend to see that those pulses follow a log normal distribution. And so even from that distribution already, it's quite rare for you to have a pulse that's, let's say, 100 times brighter than the average pulse. And so I guess originally that allowed us to think of giant pulses as pulses that lie beyond some threshold. So let's say if they were brighter by 100 or 1,000 times the flux density, then we thought of them as giant. However, the more giant pulses we found, we were able to, of course, also look at their statistics and distributions. And since we tend to rather discriminate between normal and giant emission through exactly this flux density distribution that they follow. So the giant pulses, they follow a power law distribution, which is different to what we see for this normal distribution. I finally found my cursor, I hope it keeps. And then this difference in distributions, of course, that sort of is testament to something underlyingly quite different. And so I've just put unknown for both of these emission mechanisms. Of course, that's not quite fair. There's a lot of very detailed work going on, and we learned quite a bit about giant emission from Alex's talk, but we tend to think of these two groups as being separate in the way in which they're created. So there's only a handful of pulsars that do emit giant pulses. Interestingly, many of them are the older MSPs, and so except for the crab, this is the only other young pulsar emitting giant pulses. Okay, on to the Meerkat data. So basically we searched 3 2-hour L-band epochs for giant pulses from this pulsar. So for those of you unfamiliar, Meerkat operated from South Africa in a semi-desert Karoo area. It's mostly operational at L-band at the moment, so running from 865 to 1.7 gigahertz, and it's a 64 antenna interferometer. And so it's 7 to 8 times more sensitive than the original Parkes observations. And so it was this pulsar being in a distant, in the Large Magellanic Cloud was the ideal test bed to test out Meerkat sensitivity. And so we still rely on X-ray ephemerides to analyze radio data for this. We de-dispersed it by a known dispersion measure, so that happens coherently in the Meerkat backend. And basically what you end up with is pulsar, single rotational pulsar archive files, and working through them, trying to find giant pulses. And well, of course, as a fast radio burst community, you're very familiar with trying to find signals. And in this case, it's a lot easier because already, at least we have a known dispersion. But yeah, as it shows in this graphic, like mainly you see nothing. Perhaps you were paying good attention and you spotted that one there. The first 2-hour data set of this pulsar was analyzed by an honor student, Jones Shalufia at the University of Western Cape. And so he found about 200 pulsars in that first epoch. And then combined with the 2 other epochs, we have a total of about 865 giant pulses. So that already was a 100-fold detection increase over the published work from Parkes in 2004. So really quite exciting. And the first thing we do from this set of pulses that we selected for having a signal to noise ratio larger than 7 is that we check that it follows a power law distribution, and whether we therefore think that the population we selected is in fact GPs or giant pulsars. So as you can see here on the lower left, this is the flux density distribution for all these giant pulsars, the 3 epochs combined. They do seem to follow a power law distribution with the alpha index of about -2.7, which is quite steep. And in this plot, it's the cumulative distribution, and it's just plotted with respective various reference flux densities. So on the x-axis at the bottom, it's expressed in terms of the what I'll call the integrated rotational flux density of the pulsar. So the flux associated with every rotation on average, or in the top axis, it's expressed as the sort of the mean giant pulse flux density, which is about 3.4 millijanskis. The pulsar tends to emit its giant pulses in sort of 2 phase emitting windows, which I'll call the leading and trailing phase windows. And you can see the windows here, they're quite broad. This is the integrated pulse profile over 2 hours. The very brightest giant pulse that we found is this one here. It had a signal to noise ratio of over 400, or about 800 times the rotational density of the pulsar. The pulse's duration is clearly unresolved, and it's quite scattered. But if we were to assume that our bin resolution, which here is about 50 microseconds, is the pulse width, then we find a fluence of about 4.1 Jansky milliseconds. And of course, if this pulse were at the distance to the crab, you kind of increase that by over a 600 factor fold. And if you scatter correct, this peak would have a peak flux of over 100,000 Janskys. So this lies kind of 1 order smaller of the very brightest crab giant pulse that's ever been discovered. Another interesting thing to note before I move away from this plot here is that you can use, if you trust your power law description for these giant pulses, you can ask yourself, well, to what low flux density values do I have to extend this power law to be able to account for all the flux density that I observed across the full 6-hour observing epoch, so the integrated flux density. And interestingly, if you trust this description here, you find that you have to extend the power law up to a value of about 0.1 millijanskys to account for all the flux that you aggregated in total. And the 0.1 millijansky down to which you would have to extend it is exactly the rotational, the average rotational flux for this pulsar. So it's painting a picture that you could account for all the emission you're seeing from this pulsar just through sort of low-lying GPs, or at least emission that stays on this power law. And that picture is kind of strengthened when you look at some of the other comparative properties between the integrated profile and the giant pulses. So on the left here, these are again what the 2-hour integrated epochs look like. You always have this double peak structure. For the last 2 epochs, we've got full polarimetry. And so this lower phase bin resolution is the August data. And you can see a sort of a low-lying linear polarization fraction. On the right-hand side, I'm now looking at what all the single giant pulses are doing. And if I plot their fractional polarization, I too see that they are standardly quite lowly linearly polarized, which is a bit odd for such a high E dot pulsar. But that matches up well with sort of the integrated pulse profile. And moreover, if I just here at the top here, I'm just plotting all the giant pulses that I receive from this pulsar in these 2 phase emitting windows. They're always only coming from one and or the other window. In the couple of cases where we see double emission, that fits right in with statistics. So if you were to either stack this as a histogram or just look at the envelope of these giant pulses and ask yourself, what's the average GP looking like, then it can be estimated through this black line here, and overplotted is again just the average pulse shape that we observe when we integrate over 2 hours. So not just GPs, all the emission. And you can see a very clear similarity there, having normalized the peaks. And so we're starting to think that we are not seeing normal emission from this pulsar. Most interestingly for this conference are these curious burst morphologies that we're picking up. And so the meerkat bandwidth is allowing us to kind of pick out these band limiting pulses from this pulsar. You can see a spread of them here. This is the first time we see such emission from any pulsar except for the crab. And you can see that in these plots, if you look at the frequency response, they are often easily fitted with a single Gaussian response. Here you can see the sort of the sigma widths and the center frequencies. And we also test their band limitedness, if you will, by checking if I just integrate the parts of the band where there's no clear emission, whether or not I see any signal. And in most all cases, this gray here represents the average profile over these frequency bands. I don't see any emission here nor here. Only in the very brightest band limited pulse that we have, this one's got a signal to noise of over 140. It seems that even if I'm just integrating this top couple of frequencies, I'm still getting a bit of a pulse shape, and so there could be leakage into the other frequency channels. I can also investigate the polarimetry for these pulses. So in total, from the 800 or so giant pulses, there's only about 25 that show these incredibly knotted structures.
About 1 minute left, please.
Thank you. And so most of them show high linear polarization fractions, not unlike what we're seeing for FRBs. And in this plot below, you can see sort of the distribution of the widths and their peak frequencies. Okay, so let me skip on a bit faster because I want to show to you that we also see these very unlikely sequences of emission. In particular here, we see 4 GPs in just 6 rotations. And we conclude that just through chance, this would only happen once in every 7,000 observations equal to our data. And so we wonder whether this could be testament to some clustering. And in fact, we also look at how quickly we change from broadband to narrowband features. Like here, it's only happening in 2 rotations. And then importantly, we ask, well, could this be, is this intrinsic to the pulsar or is it lensing? And I have to do this pretty quickly, but because we have a lot of information about the surrounding environment, we can ask, is this just a lensed signature from the supernova shock boundary, which we know to lie at about 0.7 parsecs away from where the pulsar is. And you can say, well, if this is a lens signal, the size of the knot gives me a handle on the lens magnification M, and I know that this lens signal must persist for at least 1 lens size resolution, some characteristic size of the lens. And we can get back to this maybe in the questions, but the lens size resolution, taking into account the distances and the observing frequency, is about 20,000 kilometers. And so if the pulsar is moving at a sort of a typical 100 kilometers per second, then that would still persist for a few minutes. Why is that happening now? What are you seeing? So let me zoom in. I don't know why that screen just started changing. Weird. Fit slide. Maybe I can take my notes away. You can just see my notes. So the lens signal would have to persist for a few minutes if it was indeed lensed, but we see rapid changes of less than 2 seconds. And so we think this is intrinsic to the pulsar. So here, I'm going to skip over because you're quite familiar with this stuff, that the only other place where we see flux knots are either in the crab or, as you well know, in repeating FRBs. And I put up some of the similarities here. Most interestingly in these last talks for me has been that but also radio and X-ray coincident emission is a big part of the neutron star model, which is we certainly see for this pulsar, and also from Daniele's talk yesterday that we're starting to see rotational periodicities in some of the repeating FRBs. So I'm sure I've run fully out of time now. Let me end. This is kind of the summary that we see resemblance with FRBs. And of course, all the details that you can find in the paper, or you can contact me.
That's super interesting. I have a lot of questions, but I think I don't see Marisa online, unfortunately. So I think I will have to ask them of her in the Slack channel. But let's see. Yeah, so unfortunately, Marissa's not around to answer questions from the Q&A. I see Brian has put a question in the Q&A, so I would suggest that we address those questions to Marisa in the Slack instead. I think I saw her pretty active in there after the first session, so maybe some of your questions have already been answered if you scroll up a bit. So I encourage you to check that out. And then we will move on to the last talk of the session. Here we actually do have our speaker on hand. So we're going to play the recorded version of the talk, which is a talk by Dongzi Li from Caltech. But Dongzi is online. So if you have questions, and encourage you to put questions in the Q&A. Hopefully you've been saving them up this whole session, and now you can ask them all, ask lots of questions for Dongzi, but we will play her recorded talk and then go to the Q&A afterwards. So go ahead and start.
Hi everyone, this is Dongzi. I'd like to talk about the emission properties of periodic fast radio bursts from the motion of magnetars. So as introduced lots of times, CHIME is a powerful telescope for searching fast radio bursts. It has 124 beams surveying the sky daily, which provides us this great opportunity to search for long-term periodicity. It not only increases the efficiency of follow-ups, but also provides us crucial information about the progenitors. We perform regular searches on CHIME repeaters, and currently the most sensitive window for long-term periodicity is 10 to 100 days. Chat with me about the constraints. And last year, so we all know that we found a periodic burst of 16 days period on our most active repeaters. Till now, it has been almost 3 years, and that source is still loyally follow the periodicity and with P dot consistent with 0. And the discovery of this period provides high efficiency for follow-ups, and the highlights are it has pushed down the lowest frequency detection to 120 megahertz, and which may influence the design of future surveys. So not only about this, but also the existence of this 16-day periodicity is very interesting and important to study. It's generically believed that this has to be related to some rotation motions, either the spin or precession or orbital motion. And the existence of this period is very curious because, for example, if it's a spin, then 16-day spin period is super long, and you still have to generate powerful bursts. So how can you preserve a large magnetic field but still effectively quickly slow this spin down this object? And also for precession, the existence of free precession is always under debate. It is very useful to explain some of the profile behavior in pulsars, but it's very curious how you can preserve this kind of free precession, given that the superfluid in the neutron star crust may quickly quench this kind of motion. And it will be a non-trivial thing if it can be proved that an object can indeed like free precessing, like this neutron star, this magnetar can indeed be free precessing. And also for the orbital system, like it's likely that the generation of the burst can be related to the companion's influence, and this will be extremely important to understand if this procedure, how this procedure is happening. So therefore, it's very important to distinguish this and verify or disverify these models. And in the last year, there are lots of nice observational constraints. The most powerful one is that the unexpected active window shift against frequency discovered by Aperitif and Loeffler. And also it is seen that the polarization angle across bursts at L band doesn't change. And other wavelengths follow-ups seems to see that this source seems to be offset from the peak star formation activity in the nearby regions. And period derivative is a very powerful source to distinguish different models. However, currently we, especially for young free processing magnetar, which lots of models expected to be very young, and the magnetic field is very large, so that the free precession is not quenched by this kind of superfluid, which will expect a large period derivative. However, currently we still haven't seen any period derivative, and current 3 sigma constraint is the p dot is smaller than 10 to the minus 4, which suggesting that the source is probably older than 100 years. Although it's a very informative measurement, but it probably takes another 10 years for it to be interesting enough. So I'd like to talk a bit more about this active window drift against frequency, because it's very interesting. Like first, it directly rules out this eclipse model, because it is seen that the low far active window is much behind the L band active window, means that when the burst can still be seen in lower frequency, it no longer can be seen in higher frequency, which is opposite of the eclipse models. So it's nice that at least one model is out. And also another thing is that this kind of, like, none of the rotation motion, the spin, the precession, or the orbital, it won't care about the frequency. It's the same for all the frequency. So if you want the active window to change against frequency, it seems to suggest a kind of shift of emission region against frequency, because that is something that generically you would expect it can be frequency related, while the rotation motion won't be frequency related. So talking about the change of emission region against frequency, another natural thing to think about is the radius to frequency mapping. There are several aspects to motivate us to think about this. There are lots of models predicting this radius to frequency mapping, and there are lots of aspects to motivate us to think about this. One is like the burst as well as the active window both gets larger at lower frequency. So in radius to frequency mapping, the high frequency emission happens closer to the surface. And when it propagates out, the cone gets larger, the low frequency gets emitted. So the lower frequency burst will be wider, and the lower active window will be larger. So it's natural, and it's also generically believed to be the case for pulsar as well. And also another advantage of this model is that it naturally expects a kind of downward drifting feature because of the additional paths. So it expects a kind of delay, so it will introduce a radius a downward drifting feature for the burst, and which is seen in lots of repeaters. So generically, it's natural to think about this kind of radius to frequency mapping. And postulated that you have a radius to frequency mapping, you can work out all the geometry for different models. So currently we go through models which only, which attribute this periodicity to purely geometric effect, like slow rotation, free precession, and forced precession. However, if for other models like the binary motion, as long as it's expecting some emission region change, it can be extended to that models as well. So for both slow rotating magnetar and free precession model, you can introduce offset emission region for different frequency, and it's asymmetric to the magnetic pole. Then you can introduce this kind of active window drift from the geometry. However, for forced precession, because unlike the free precession where the precession axis in the static frame of the precession axis, the emission region is fixed, is static on the body frame. So you can postulate some kind of shape of the emission region to explain whatever you want to explain. However, for forced precession, in the static frame of the precession axis, the emission regions is rotating against the rotation axis. So when the rotation period is much shorter than the precession period, basically the emission region will look like rings centered at the rotation axis. So for wherever you put this line of sight in, the emission rate, the active window change against frequency has to be symmetric against its center. So this is an example. So for slow rotating magnetar and free precession, you can have this, you can introduce this drift of active windows, while for forced precession, the window is symmetric. So it's kind of against the observation fact. And another constraint is the polarization angle. So polarization angle has to be static at L band, which suggests that the line of sight is far from the magnetic pole. And also polarization angle is something that's very straightforward to constrain different models. So for slow rotating magnetar and models at a given phase, the polarization angle is fixed. While for free precession, at a given phase, the polarization angle can appear to be of various values related to its rotation phase. So here, the three colors indicates emission at different frequencies. So both cases, you expect some change of polarization angle against frequency. And this is a very strong constraint. If the polarization angle stays the same against frequency, then both models will be disfavored. So in summary, so this kind of long-term periodicity of fast radio burst provides great values for us to understand the progenitors. And the chromatic active window of this fast radio burst 1809-16b likely suggests a change of emission region across frequency. And this small PA variation seems to suggest that emission is far from the magnetic pole. And the polarization angle measurement across frequency can be a very strong test of different models. And we are trying to perform multi-band observation of this source with GMRT, which you can see from Surya's lightning talk. And also another interesting to think about is like if the free precession and the slow rotating magnetar model are both disproved by this polarization angle measurement. And then the leftover is the orbital motion model. And we know that for the orbital motion, all the passive models like pure eclipse or forced precession, where the generational fast radio burst has nothing to do with the companion, all those models seems to be disfavored by the chromatic active window. So the leftover is suggesting that if it's orbital model, it's likely that the generational fast radio burst is due to some interaction with the companion, which is non-trivial. And also it links back, it makes us think about the recent discovery of globular cluster fast radio burst, where in the globular cluster, well, there are more binary interaction, and it will be very interesting that these two sources may be complementary to each other for the study of the nature of the fast radio burst. So in summary, so it's generically very valuable and fruitful to study this source, and it can provide us even more clues if we keep looking at it. And thanks very much.
It was a really, really interesting talk, Dongzi. Thank you so much. Okay, so we have a question in the Q&A already from Vishal, who asks, don't you also expect the pulse widths to follow radius to frequency mapping across frequencies? Maybe I'm not aware, but has that been seen?
I think it's already seen that lower frequency, the pulse width gets larger. I'm not sure how should I address this, but yeah, but I think at L band the width is probably less than 1 millisecond, and at time band the width is probably a few milliseconds, and at lower band I think it's less certain because there are scattering, but it's certainly much wider.
Yeah. I guess it's hard to tell. Well, you'd have to separate out the effects of like the scattering and the instrumental effects, but I do think it is wider at lower frequencies. Okay, do we have other questions in the Q&A? Is anyone? I don't see any right now.
Maybe I can ask a question live since I can unmute.
Yeah. Go ahead.
So Dongzi, your last point about the binary systems, why necessarily interaction? Couldn't one have, for instance, like a swept back magnetosphere in a binary system, which you have radius to frequency mapping, but then the modulation at the 16.3 days is still the orbital period? Do you necessarily need there to be interaction in the binary system?
Sorry, I didn't quite understand the question.
So still in the context of considering radius to frequency mapping, but instead of having precession, having that modulating the activity, just binary motion, and you're looking at basically different emission regions in a swept back magnetosphere, where it's swept back because of orbital motion.
Yeah. So what's the question? Sorry.
I guess the question I'm getting at is, in the context of a binary model, does one necessarily need interaction, or could you still get it to work with a non-interacting binary system?
You mean still geometric effect or eclipse?
Yeah, it's just a geometric effect, except for the geometry is changing because of binary motion instead of precession, for instance.
Then how why are different frequencies are different if it's purely because of the binary?
Well, it's still radius to frequency mapping, and your line of sight to the different emission regions is changing in time because of binary motion instead of precession.
Oh, I see. So okay, so let me try to get it. So you have a radius to frequency mapping, and then you still want some eclipse mechanism because you want this swipe back like a few.
Not necessarily an eclipse, just beaming, for instance.
It's let me think. But why would that be? I think you can expect some profile widening at lower frequency, but it's not obvious to me why it will be a shift in this case.
Let's discuss it offline. I can make a sketch. Maybe it would be easier to make a sketch than try and trying to describe it in words.
Okay.
Okay, thanks, Jason. Any other questions? Nothing new in the Q&A. In that case, thanks, Dongzi. Thank you to all of our speakers, both live and recorded, from this session. Very, very interesting stuff. We can conclude the session a little early, just to remind people that immediately following this session for the next hour, there's coffee and tea in the Gather Town for those who have coffee and tea, or if you're like me and it's 6 p.m., maybe bring a drink and come chat with us in the Gather Town if you have a chance. The other thing to note is that we have our first discussion session in about 2 hours time. So discussion session 1A about exploring the parameter space of fast radio transients. And that will be led by Liam Connor, Kendrick Smith, Sarah Brooks-Ballore, and Keith Bannister. So please join us for that discussion, talking about ways that we could be looking for FRBs and what areas of the parameter space we should be exploring. So join us there or join us at the coffee and tea, and we'll see you at an upcoming session. Thank you so much for joining.